Hello. In this lecture, we will discuss the ramp wall thickness design. Now, as we've discussed before, I'll reiterate, ramp walls serve the following purposes from a structural perspective. They are self-weight, resist sliding. They serve as compression struts that transfer cable forces from the anchor to the tiers and foundation and tower structure, which we discussed in the previous set of lectures. And 3, they contain a fill material, so are almost a formwork for the fill material to further resist uplift and sliding. Now, item 3 we'll address in more detail. Item 2 is discussed previously, and item 1 is also addressed in the advanced stability checks when we talk about how to calculate the self-weight of the ramp walls. During the construction process, ramp walls are built and backfilled with 30 centimeter lifts of stone, gravel, and grout, collectively referred to as fill. This fill can result in a lateral hydrostatic pressure on the ramp walls, similar to how we consider P active on the back of the abutment, or similar to if you've ever done concrete formwork design. The concrete wants to spill out, it's creating a pressure distribution on the formwork that we need to consider. And to counteract this lateral pressure, we stagger the masonry wall thicknesses based on abutment size, or more specifically, the maximum height of ramp walls from grade, which corresponds and correlates to abutment size. And the maximum height of a ramp wall is measured from the walkway saddle, which is 40 centimeters above the top tier for standard, to ground level at the away from river face of the foundation. And we can draw that crudely here down to ground level. That dotted line is what we're talking about, and I'll show that again. And you'll notice for standard abutments that one tier will never rise more than 1.4 meters from the ground, 2 tier will never more than 3.4, 3 tier 3.4, etc. Now, from this and empirical evidence, we can derive a series of rules to follow for all custom designs. And this is to ensure internal stability when adjusting the abutment geometries so that the ramp walls don't crack, they don't fall over. And we'll do that actual calculation in the following sections. But first, we'll go through this set of rules, and we'll let H be in these rules below, be our maximum ramp height from ground level. So first, we'll ask, is the maximum ramp wall height above ground level less than 1.4 meters? If so, this corresponds to the one tier standard. We only need 30 centimeter thick walls. If no, we'll look at if it is between 1.4 and 2.4 meters, which corresponds to a 2-tier standard. If so, we need 30 and 50 centimeter thick walls. And following this figure here, we'll draw a vertical line 1 meter down, and then a horizontal line until it meets the ramp cap, the back wall, or the anchor, doesn't matter, and that will be our area of 30 centimeter wall using the level method, which is talked about in the previous section, and the rest will be our 50 centimeter wall. Now finally, if it is between 2.4 and 3.4 meters or a 3-tier, and this could actually really be 3.9 meters if we have a 1.5 meter tall foundation. And if it's between 2.4 and 3.9 meters, we'll follow the same process. We'll draw another, 1 meter down and across for our 50 centimeter wall, and then our 70 centimeter wall will be the rest. Now, one last potential issue here, or I note that anything greater than 3.9 meters is not allowed by this empirical rule and should be discussed with your DEIC. And one last potential issue here is a special case in which the foundation is 1.5 meters tall. With these special cases, there's a chance you'll be adding a 70 centimeter wall to a 2-tier size foundation width. And in this case, the ramp walls will extend past the foundation. And you can see that here in this screenshot. So for the calculation purposes, we will not be including ramp wall that overhangs the exterior of the foundation to contribute to sliding forces, as seen below.